Okay, so now we're going back to the chapter 15 Excel file. This example is from your book, and I just did it in Excel instead of manual calculation. Okay, so so we're talking about the McDonald's. So here's a similar place, Burger Dome, fast food restaurant, and we are told the arrival times are random and unpredictable, so we could assume it, and it will be, it resembles like kind of Poisson distribution, so it follows a Poisson process. And on the average, 45 customers arrive per hour. Okay, so here we could say, let's see, lambda was the arrival rate, right? So lambda is 45 per hour. Okay, and it says service times are random and unpredictable, and service times are assumed to follow exponential distribution. On the average, it takes 1 minute to serve a customer, and the manager is concerned the waiting time of the customers might be excessive. Okay, so these kind of fast food places, and a lot of places like to keep the time in the time, like the time to, let's say, they will limit the time the customer spends to about 3 minutes, to no more than 3 minutes. That's the kind of standard in many places. So we want to, but the manager is thinking maybe it's a little bit higher with the current operation. So there is, I don't know if I mentioned here, I guess maybe I forgot to mention, there is one server here. There is one server, so you got here customers waiting, and then you have here counter with a cash register, and here you have this one server, can I take your, saying can I take your order? And then you got this, back here there's all these people making stuff, making fries and putting together hamburgers and so forth. But we're not going to count those people because they're not having a direct contact with a customer. Okay, so we're going to count this person as our server. So there's only one server here. You got the customers. Okay, let's say here's the one being served right here. Okay, so we want to see how long these customers are spending in the queue, and also maybe in the entire system. So remember, like this part is the queue. Up to here. Up to here is a queue, and this part here is a service area. And we want to see how long people spend here, and then combine that would be the entire time, in the system. Okay. And it says it takes 1 minute to serve a customer. So already we're told that it takes about 1 minute here. So on the average, people spend about 1 minute receiving service. Remember the service time, we use this reciprocal of the service rate. And so 1 over mu is 1 minute. 1 over mu is 1 minute. So then, okay, here's a trick question. Then what does it say about mu? So it's 1 over mu is 1. Then what is mu? Right, 1. Right, 1, right? So 1, therefore 1 here, I get 1. So 1 per minute. So mu is 1 per minute. Okay. And it says, who's he? He is the manager, I think. So the manager, oh, there it is. Manager wants to analyze the performance of his waiting line system. So how am I doing, kind of thing. So how is our system doing? Is it running efficiently? Customers are not waiting too long, that kind of thing. So the performance measures are called operating characteristics. And there are things like how long people wait, how long is the line, and so forth. Okay. So we're going to compute the operating characteristics, and then we'll consider some other options. So first, we're going to take a look at this. Now the inputs we need are lambda, mu, and the number of servers. So the arrival rate, service rate, and the number of servers. And so we have the mu here as 1 per minute. Now we have the lambda here is 45 per hour. Okay, what is wrong with just using these? 45 and a 1. So I'm going to put these into formula. Yes, Jeff.
Would it be that an hour is 60 minutes? You really can't compare.
Right. It's like comparing apples and oranges. So you need to have the same time units, right, for all the weights. So I could either convert this to per hour to match this, or convert this to per minute to match this. So either way, will work. And in the book, they use the minutes, so I'm gonna go with the minutes. I gotta be consistent. So 45 per hour. So I'm gonna convert this to per minute. Okay, so the conversion factor is 60. Okay, question is, do I multiply by 60 or divide by 60? Divide, right, because I want to make the number smaller. Per hour, and the per minute would be much smaller, so I gotta divide. So 45 divided by 60 gives me 0.75, so I would say 0.75 per minute. 0.75 per minute is the arrival rate. Okay, so it means that like in 1 minute, not quite one customer comes, like 3/4 of a customer come in 1 minute, but it's an average number, so it's okay to have decimals. I mean, you expect to have the decimal digits for averages. So 3/4 of a customer per minute, and mu is 1 per minute. Okay, now we're going to use these. Lambda is 0.75, mu is 1, and then how many servers here? We got this one guy right here, and that's the k. K is the number of servers, so we'll say k is equal to 1. Okay, so this is a kind of notation we use. So this 1 here means, well, one server, single server system, and the this, and there's, okay, I don't think you guys are interested in knowing what these things stand for, but just know that it just means that Poisson and exponential. So this first M means Poisson arrivals, and this other M means exponential service. So basically it just means you can use the formulas that are given here. Okay, and because it says right here, they're the keywords, Poisson process and the exponential, so these two words mean that you got kind of system. Okay, now here is a kind of, so what I did, I've made a kind of separate sheet for each variation, but well, time is short, so I'm gonna go to the sheet that has everything, which is this one. It says MMK with all options. So this has already been done. I sort of been done. So what I'll do is I will make a copy of it, so we could at least do some work on it. So we're gonna create a copy, and then okay, and just say yes. Okay, and I have. Okay, so there's something like this. Okay, so let me show you let me explain what this is. Okay, so this one is this has a formulas for multiple server systems. So it works for 2 servers, 3 servers, but it also works for 1 server. So actually, it works for whether you have 1 server or more than 1 server. And then this one, the formulas here, these are only for 1 server. Okay. And so you got kind of these kind of formulas here, and then with a okay, and then these are the formulas for multiple servers. But if you just plug in, like over here, K here is the number of servers. So if I just plug in 1 here, wherever you see 1, and it just turns into the formula for a single server. So it's okay to use multiple server formulas. If you have 1 server, it'll just work out the same. So we'll just save time and go to the multiple server system, the formulas here. Okay, and when you see these formulas, so this is kind of like you gotta get this thing called P sub 0, and then from that I get that, and so forth. So it's a little complicated, but especially this part. There's all this stuff that. It's got the sigma notation. You got the somebody's screaming here. Oh, it's factorial. Oh, we got the factorials here. So like lots of calculations. Somebody wrote a macro for this, not me, but somebody else did, and stuck it in the file. This P sub 0 here it just looks like this. So it's just a function that's defined somewhere else in the file. It's like it's by some macro that's been defined in the file. Okay, So that's where the macro is. And so it is just compute. It's not. This actually represents this big complicated formula that was defined in some other place within the file. Okay. So let's see. We're going to. The green part is supposed to be the input part where I put in the data, and let's also delete this part here. Actually, I should make this part. This part green. And write this. Okay, because I need to put in numbers here too sometimes. Okay, so that's through here. Okay, now first I'm gonna say original. Original, which is number 1A. Okay, number 1A is what we're going to analyze first. So remember, number of servers was 1, and arrival rate was 0.75. So I just print 0.75. Service rate was what was it? What per minute? 1, right? 1 per minute, and it tells you everything. So here are the results, and these are the operating characteristics. There are 6 of them here. So and there's definitions right here for your convenience. So P sub 0, probably that no customers are in the system. So what this means is about 25% of the time there is no customer in the system. So it's like place is empty. Or like the server is just sitting there doing nothing or doing something else but not serving the customers. So 25% of the time. And the average time a customer spends in the waiting line, that's called W sub Q, and that's 3 minutes. So this is one of the key measures. So average time a customer waits in line is 3 minutes. Okay, now if average time a customer spends in the system, that's the W, so the different notations, and that's 4 minutes. That's 4 minutes. So let's take a look here. Let's kind of remind ourselves what a system consists of. A system has, right, you got the queue, and you have the service. So if I were to talk about like average time, this part is W sub Q, how much time customer spends in the queue, average, on the average, and how much time the customer spends receiving service, that's 1 over mu, and WQ here is 3, and 1 over mu is, we already know is 1 minute, is 1 minute. So if I add 3 plus 1, then if I add this, I should get 4 minutes, and it's, oh yeah, that's what it is, 4 minutes. That's 4 minutes. So 3 plus 1 is 4. If you take like, average, this average number, the average number, and add them up, you get the average of the sum. Average of the sum is like sum of the average of the sum is sum of the averages, and kind of property. Okay. Okay. And then what are these things? LQ and L. So if you want to know how many people are in line on the average, well, it's going to vary from time to time. Sometimes you have nobody in line. Sometimes you have 5 people in line. But if I were to like take a look every second, record how many people are there, and if I were to average all those data I took, that would be the LQ, the average number of customers in the waiting line. That is 2.25, so it's 2 1/4 of the people. And of course, it's decimal number because it's it's the average. It doesn't mean that you have 2 full-size people in line and then followed by a little toddler, quarter size of the full adult. So it's like you were saying, the average family has like 2.2 children, but you never walk into some average household and then find the 2.2 children. You just get whole number of children. Okay. And then L is the average number of customers in the system. So that would be like, that would include the person receiving service. Okay. So if I were to ask, okay, what's the average number of customers in these places? So there would be LQ would be here, and actually this number of people in the receiving service actually lambda over mu, and if I were to add these together, I would get L. Sorry, it's kind of hard to see. L. L is includes the people in line and the person receiving service. So LQ is 2.25, and lambda over mu is lambda is 0.75, mu is 1, that gives me 0.75. If I add these two together, that gives me L. So 2.25 plus 0.75 gives me 3, as it says, as here. So 3 people in the system on the average, including people in line and the person receiving service. Now, now again, this is decimal number because sometimes you have nobody receiving service, so you have 0. Sometimes you have 1 person receiving service. At the average, the zeros and ones, I get 0.75. And then what else? The last thing is P sub W. Probably an arriving customer has to wait. So if you are, let's say, going to this burger place and you're in a hurry and you're really hoping that you don't have to wait, you're wondering, what's the chance I'm gonna wait when I get there? That's this value, 75% chance that you will have to wait. Okay. Okay, so these are the kind of performance measures that we want to compute, and then we try some other option and then compare how these numbers do compared to the original system. So so far what we have is the average time in the system is kind of 4 minutes. So it seems a little bit long for a fast food restaurant. So now the manager wants to improve this by considering an option by spending some money by hiring somebody else. And so, oops, let's go this way. So to reduce the waiting times, the manager would like to try hiring an order filler who will assist the order taker. So you got two jobs, order filler, order taker, but they handle the same customer. So these two servers work together to serve the same customer. Because there are 2 people serving the customers, it's going to go faster. Service will be faster. So instead of a service rate of 60 customers per hour, now it will go up to 75 customers per hour. It's 60 per hour because it's 1 per minute, so it translates to 60 customers per hour. So, so what happens is you have here 2 servers working together as a team, serving the same customer, and here's a counter, and like this. So you got the customers here, this customer is receiving service from both of these people. So this is still considered a single server system. Since as long as the 2 people have to serve the same customer, then you would say these 2 people form a team. So it's just 1 server. 1 server made of 2 people. Okay. So it's MM1, a single server, and so here K is equal to 1 when we put in the values. So what happens here, this is the service rate, so it's 75 per hour, so we just translate it, convert it to per minute, so 75 divided by 60, we get 1.25 per minute. Okay. So that's what we put it, 1.25. So let's go over to where we were before. So here we're going to say number 1, what sheet number 1, and then part B, and number of servers is 1, and the arrival rate lambda is the same, and service rate is, what is it, 1.25 per minute, and now we have all these results. So, of course, you're spending more money, so you would expect things to go faster. And here are the results. So here we got the average waiting time is now only 1.2 minutes, and average time in the system is only 2 minutes. And these numbers are also smaller, so we could definitely see investment has made the system more efficient. Okay, so I was going to say MM1 with 2 employees. Okay, some kind of label. Okay, so that's this part, and then now let's consider something else. Number 2, it says another alternative. How about, will it be even more efficient if we get if we have 2 registers, so that these 2 people could work kind of separately, so they could do like parallel processing. They could serve 2 customers at the same time. Okay? So this will be a multiple server system. So what you have is we have line. Here's a, okay, well, line, sorry. And here is a counter, and you got here 2 customers being served, and you have 2 servers, and you got 2 cash registers here. Okay, so this is like bank situation. You have 1 line, and the customers can be, each customer can be served by the first one or the second one, depending on whichever which one becomes available. So here the 2 customers can be served simultaneously by these 2 separate servers. So this would be considered MM2 because you have 2 customers can be served at the same time. Okay. Now here, now what are these? So we could say k is equal to 2, and lambda is still the same, which was 0.75, and mu is supposed to be the rate per server, Okay, so it's gonna be just the same as the original mu, which is 1 per minute, 1 per minute. Okay, so it's not supposed to be the combined service rate, but the separate service rate. If you have 2 people working together, like like this, then the mu is the combined service rate. And then your 2 people work together. It's faster, and so mu is some kind of higher value. So mu is higher this way. But here, if 2 people are working separately, we have to count each person's service rate as the mu. Okay, so mu is 1 per minute. So we put in these numbers, 2.75 and then 1. So we're going to go over to here, and then here I'm going to put 2 at 0.75 and then 1. Then what's the what kind of numbers do we get? Okay, so WQ is well, that's much smaller. 0.16 minutes, so like hardly nobody waits. So 0.16 minute waiting time, and time in the system is 1.16 minute, and so forth. Average number of customers waiting in line is only 0.12, so lots of times there will be nobody waiting in line. Okay, so things are even faster than before, just with the investment on the cash register. So extra cash register, so that's not bad. Okay. Now that's all great, but let's think about, let's label this too. This is number 2, and this would be MN2 is what we just did. Okay. Now that's all that's all great, but then what about the cost? If you have 2 people you have to pay, of course that incurs higher cost. You could always give better service by providing lots of servers. So if you have more employees serving the customers, then the customers will not have to wait at all. But the downside is that you have to pay all these employees. So you strike some kind of balance between 2 extremes. Really good service but high cost, or the poor service but low cost. Okay. So we want to do some economic analysis of this situation. So we want to consider both the cost from making the customers wait and the cost of providing service. The money that you have to pay to your servers, and then the kind of indirect cost from making the customers wait. By if you make the customers wait for a long time, you're going to incur some bad feelings. So there will be some loss of goodwill, and the customers might not come back. They might tell their friends might tell their friends, and so forth. And maybe you run out of here, you go out of business, because nobody will come to buy burgers at the Burger Dome. So we need to consider there is some cost associated with making the customers wait, and sometimes it's easy to estimate. A lot of times it's hard to estimate what is the actual dollar amount lost by making the customers wait. For our case, we're just given the estimate, and we just have to do the kind of simple calculation by using the given numbers. Okay, so let's see what that is. This is the okay. I'm not going to go through all this explanation of waiting cost, and because again, there's always a time constraint, we're going to basically apply the formula. So I'm not going to talk about how we got the formula, but but at least we learn how to apply the formula. Okay. So here's the situation. Now, what about the cost? The costs are given like this. There's the pay. Okay, servers get paid $10 per hour, and for customer waiting time in the system, you attribute $15 per hour. So $15, so that's like a waiting cost rate. So waiting cost rate, we're gonna call it C sub W for cost of waiting, and that's the cost of providing service, like wages for your servers. Okay, and the formula is, I don't know where it went. It was used to be here. Okay, it's like this. TC is CW times that's L. CW times L plus C sub S times S. So that's the times. And here S is number of employees. You could think of it as like servers, but sometimes server is made up of 2 people and you have to pay everybody. And so we're going to call it number of employees, like how many people you have to pay here. And L is supposed to be the average number of customers in the system, but it also works in the formula as the kind of estimating, like what is your total waiting customers do. So it actually works out, let's calculate the waiting cost. So CWL plus C sub S times S. And then maybe something else, if there's some extra cost mentioned, just add it there to get the total cost. So this part is the waiting cost, and then this part is the service cost. So when you try to reduce the service cost by laying off your workers, then your customers will have to wait longer because you have fewer servers. So this is going to go up. So when you try to lower this is going to go up. When you try to lower this, that other part is going to go up. Basically, you got to consider both. Total, the sum of the 2 parts, the sum of the 2 kinds of costs, and we want to try to minimize that sum. Okay. So how we do that is we just consider different options. It's not like you can't really put it into solver and then you can't just say, oh, give me the optimal solution, because this kind of thing is, for queuing formulas are much more complicated than a linear kind of formulas. So we have looked at 3 options, right? So the original one, and then having an extra person working together with the original person, and then the third option was having 2 people work separately. So we're going to calculate the total cost by using this formula for all these 3 systems, and we'll see which one has the lowest total cost. And that is, let's see, do I have it here? Aha, okay, here's my table for calculating those numbers. Okay, so option 1, that was the original one. Original. Okay, let's call it 1. And then 2 and then 3. This one was just kind of like this. Okay, 1 line and then 1 server. And here is a 1 line and then going to 2 combined server, 2 combined people. And then here you got 1 line kind of splitting to 2 servers. Okay, and I'm going to copy down the numbers from here that we already computed. And let me see. That's CWL plus CS times S. So I just really need the L. So L is, let's see, 3 for this one, and 1.5 for this one, and 0.0727, no, 8.8727. So these are just copied from the from here. Like these numbers, 3, 1.5, 0.8727. Okay, and okay, where am I? And I'll go back to thing. Okay, so the waiting cost is this part. So that's CW times L, and CW is 15? 15. Okay, waiting cost $15 per hour, and that part is 10. Okay, so 15 times 3 is 45, and C sub S times S, and that part is only one server here, so only one person to pay, so 10 times 1 is, well, 10. So 45 plus 10 is 55. So just add them, I get 55. Okay, and the waiting cost for this one, the second one, here you gotta pay 2 people. You gotta pay 2 people, so here the service cost will be double. 10 times 2 is 20, and this one is 15 times 1.5. 15 times 1.5 is $22.50. Okay, and then I just add them up. 22.5 plus 20. 22.5 plus 20 is $42.50. Okay, so far this is lower. Now this is lower than the first one. And let's talk about this one. 15 times 0.8727 is $13.09. $13.09. Then here I still got 2 people to pay, so same as this one, $20. And adding that gives us $33.09. Okay, so it kind of makes sense. It's like, you know, these 2 service costs is the same, but we know that this one is more efficient, you know, like lower in the waiting times and so forth. So it makes sense that you have total cost that's here lower than the second one. Okay, so this one is the best, most economical, you know, cheapest, lowest cost. So considering both the waiting and the service cost, we would conclude that let's go with this option, the third option. Okay, any questions? Any questions? Okay, so that is basically the kind of questions that we want to think about, like comparing systems. Okay, and let's see. I will also mention here. So on the homework, you will be asked to try different options. So in some question, it might say, you're asked to try some numbers. It might not give you like how many servers to try. You just gotta kind of play around with it, and there might be some kind of like criterion. So one thing I want to point out is there is certain number of servers you need to have to function. Right? If you don't have enough workers, then the customers are going to wait forever, and eventually you're going to lose the customers. So there's a certain minimum number of servers you need to have in order to process the incoming work, in order to process the customers at a reasonable time. And that's this condition. So how many servers do you need? This is called a utilization rate. So basically, how much of the server basically like how busy are the servers? How busy are the servers? So this is a ratio between different rates. The lambda, is the arrival rate. So this is like lambda is how fast the work is arriving, how fast the customers are arriving. Okay, so that measures how fast customers are arriving. So it's like the input to the system. There's work coming in. How fast is it coming? And the k times mu tells you how fast you could process the work. Because mu is a rate for a single server, and the k is how many servers you have. So k times mu is basically your capacity, how fast you could do it. When you have all the servers, if you have all the servers working at the same time. So how fast you can process the customers, or how fast you could serve the customers, given you have k number of servers, and you want to have enough servers here so that this denominator is higher than the numerator. Okay, so you gotta have enough capacity to serve the incoming customers. So what you need is something like this. You need lambda less than k mu, or you could say k mu greater than lambda. Okay, so how fast you could do it must be greater than how fast the work is coming in. Or another way of putting it is k must be greater than lambda over mu. So this is like the minimum number you need. Okay, so for instance, if let's say lambda is 3 per hour and mu is, let's say, 2 per hour, then I need k to be greater than 3 over 2, which is 1.5. So I need to have minimum unit is 2. So you need at least two servers to handle the incoming customers. So don't put 1, right? So let's say here is as an example. So let's say here you got the let me see. Okay. So let's say here I have arrival rate is 3 and the service rate is 2. Okay. And if I put a 1 here, then I get, whoa, what is this? I get negative values. So formulas don't work. So formulas are assumed that that you meet that condition, that ratio is less than 1, or that the k is greater than lambda over mu. And so if you have negative numbers, that means you're putting in too small of a number. You have too few servers, so you gotta raise it. Like 2 here, like so that's 2 is the minimum you need to have positive values here. And then let's say your goal is to keep the waiting time to less than half an hour. So if your goal is to keep the WQ to less than 0.5, and then you will say, okay, here, oh, that's not less than 0.5. And then I would try I try a bigger number, 3, and then see if that's enough. And right now that's enough. So now that's less than 0.5. So that kind of questions are asked. You know, and the kind of issues would be in the homework. Okay, and let's go now to go to chapter 16 file. Here it's kind of, let me conclude that simulation example. Okay, so let me, sorry for jumping back and forth. Let me remind you what the question was. Okay, question was, okay, no more than 1 minute. That's what we want. Okay, average delay waiting for quality inspection should be no more than 1 minute. So here, the objective or the goal is to keep the WQ. WQ should be less than 1. So this is what they want, 1 minute. Okay, and then question is one inspector enough? Is one inspector enough is a question. And if not, let's try 2 inspectors in the simulation. So here I see, here I have one inspector, okay, and then I look at here are the operating characteristics, and what are we looking for? This one, right? Average waiting time. Is it less than 1? No, not less than 1. This is, it's greater than 1 because it's 1.84, greater than 1. And oh no, it's greater than 1. So we need to try adding another inspector, and that's why we have a sheet for 2 inspectors. 2 inspectors. Okay, and I'm gonna skip all the details, and I'll just show you the result. So you won't be responsible for like details of Excel formulas in these. But if you want to study it further, feel free to do that, because I did have everything in writing. See, there's always writing. If you want to go through it and really try to understand what's going on, in the machine, you could. Maybe after the finals. Yeah, right. So here it is. Okay, so here's a two server one. So it actually happens. So it's a little bit harder. There's some other components to modeling 2 server system. You could see here. now I have some extra columns. So here I have to keep track of like these two inspectors. I have two servers, so I got to keep track of what's going on with those two inspectors. So I know which customer goes to which inspector to keep track of all that. Okay. And there's a little different, more complicated formula over here in the start service time. It has it's got max, but there's a min here. Instead of max 2 values, it's got 1 value and then some other value from the min formula, kind of thing. Okay, so the result. Let's look at the result. The result is over here, and we want to know, is this less than 1 with 2 servers? And oh, good. We don't have to do 3 servers, so we could stop here, and that's definitely less than 1 minute. So that's good, because I'm glad, because 3 servers would be even harder to model. Okay, and let's see. So okay, so we discuss all these parts. So at this point, any questions? Okay. As far as what you are responsible for, let me show you what's on Blackboard. Assignments. Okay, so assignments, and so this is you do some homework, but don't hand it in. Do a quiz based on the homework, kind of thing. And here, the quiz is. Oh yeah, it's automatically graded, so you're able to see which ones you got wrong, and before you do the second attempt. Okay, and. Yeah, I think so. Okay, so the important thing is first you gotta read this. The first file here, it explains everything. See, it says read carefully. Okay. So there is a homework that comes from chapter 15 and 16.3, and chapter 15 answers are given in a Word file that is also attached there. And you could check your answers against it, and then take the quiz based on the homework. 40-minute time limit per attempt, and of course if you already did the homework, it's not going to take you 40 minutes. It will take you much less. And you could see which, but if you didn't do the homework, it will take you longer than 40 minutes. Okay, so do the first attempt, see what you got wrong, and then do it again. The quiz has 4 questions from chapter 15 worth 6.5 points, 3 questions from 16.2 worth 3.5 points. Okay, let's see. All right, so the 3 multiple choice and 1 matching, so these are automatically graded. So basically, it'll just be, okay, you did your homework. Okay, on problem number whatever, change this little thing. Change this number and then tell me what you get for the result. What do you get for the average reading time, or whatever. The kind of similar question that I asked on the homework. So just variations on the homework problems. And chapter 16 questions. It's basically just restating the answers to some of the questions. Okay. So chapter 16. Okay. Okay. So on the quiz, it'll just ask for a few of these questions, just straight out. So there's no variation. Just basically, just give me the answers you got on some of these questions. But I mean, but do all of them, please. Please do all of them. Don't just do the ones that are on the quiz. Okay. So you'll be using, for this one, for this part here, you'll be using that black sheep example. That's chapter 16 Excel file we've been looking at, and for these others, there is a template here. which has 4 identical sheets. So same sheet we've been working on. I just made 3 more copies. Well, I just made 4 copies. So and I just number them to keep them organized. So there are 7 questions, but some of them are just paired together. They're like 2 parts of the same question. Some of these. So it's like 4 problems. So 11 and 21, 12 and 13, 20, and then 22 and 23. And you just put in the numbers in the green parts, green parts, and answer the questions, looking at the result. Okay. And there are just some numbers filled in just from the example, just as placeholders, but you would just change the numbers to the numbers that are given in the homework. Okay. Let's see if there's anything else to say about this. And please read the hints and those things carefully. Okay. And be careful with like sometimes they give you the service time. Like for instance, number 11, average service time is 10 minutes, but that's not the service rate. Right? So you got to convert it to the service rate before you put it into that the green cell in the file. So make sure you have the make sure you have the same time unit for the lambda and the mu, right? And if the service time is given, then convert it to the service rate. So like here, the arrival rate is 2.5 per hour. So it's probably a good idea to convert this to something per hour. Right? So 10 minutes, well, there's 60 minutes an hour, so that must be 6 per hour. So mu would be like 6 per hour. But either way, you could do per hour or per minute. You just have to be consistent. So lambda and mu have to have same time unit.